All right, hello and welcome. I'm going to start this for real this time. I'm Carly Anderson, chemical engineer and partner at Prime Movers Lab. I'd like to start by welcoming everyone. I see LPs, founders, some of our extended Prime Movers Lab family, and I'd like to extend a special welcome to our new Growth Fund LPs. So grateful to have you all with us on this exciting journey. So for anyone who is new, Prime Movers Lab is a deep tech venture firm that invests in breakthrough science companies that have the potential to transform billions of lives. That means we invest in the building blocks of civilization, so things in infrastructure, transportation, manufacturing, extending human health span, agriculture, and of course, our topic today, energy. At Prime Movers Lab, and particularly as a technical partner, we get to live on the front lines of deep tech innovation. So we've seen over 3,000 companies so far this year. And with these webinars, we hope to share some of the exciting areas we're thinking about and the amazing people we're meeting along the way and technologies with you all. So with that, just a few housekeeping details. Number one, I want to plug our next webinar in 3 weeks, December 8th, on the human-machine interface. We will keep this to 1 hour, so don't worry if you have a 1 o'clock or whatever time zone you live in, well, that'll be okay. We have some questions ready to give to our fantastic panelists, but we'd love to hear from you as well. So please put those in the Q&A. Also, any comments at any time in the chat feature, we'd love to hear from you. So with that, I will turn it over to my teammate, Liz Stein, to kick us off.
All right, great. Thanks so much, Carly. Good afternoon, everyone. I'm Liz Stein, systems engineer and partner here at Prime Movers Lab, and I am very excited to share with you guys today our topic of the day, geothermal energy. We did a little bit of a tongue-in-cheek with our intro music and our title for this webinar because it's one of the ways we can drill for clean energy. So a lot has been talked about for renewables with solar and wind. Geothermal is a way to do kind of sustained and tunable baseload power. So we're very excited to kind of inform the audience on this topic and in particular, some of the interesting innovations going on with drilling technologies and fracking technologies. We're also fracking for clean energy here, not just drilling for it. So we have an amazing panel of folks who are experts in this field and actively working on this. And with that, let me start the intros. I'll start first with Carlos, please.
All right, so hello everybody. Thank you, Liz. Thank you, Carly, for the opportunity to be here. I am the CEO and co-founder of Quaise, a company developing millimeter wave drilling systems to scale geothermal to terawatts. Happy to tell you about the company and how geothermal can play a huge role in the energy transition.
All right, sorry about that. I'm on mute because I have an echo in this room here. Thank you so much, Carlos. Next up, we have Tim Latimer from Furvo.
Hi, thanks for having me. Great to be on this panel with Carlos and Eli. I'm the co-founder and CEO of Furvo Energy. We're a geothermal development company that is using new technology, in particular horizontal drilling and advanced data analytics and fiber optic sensing to make geothermal drilling more cost effective and repeatable with a similar mission to Carlos. We're all kind of working on the same thing here together, which is to really scale geothermal rapidly and make it a meaningful part of of addressing climate change. By way of background, I started my career as a drilling engineer in the oil and gas industry, worked there for many years, looking at new technology innovation and new drilling techniques before I got very curious about climate change and saw the potential to drive new technology solutions forward in geothermal to have a transformative effect on the industry. So that's what got me first interested in this, and looking forward to talking a lot more about the potential of geothermal on the panel today.
All right, excellent. Thank you so much, Tim. And last but not least, Eli, who is a technology policy expert. Very excited to have you join us as well, Eli.
Well, thanks, Liz. I'm Eli Dorado. I'm a senior research fellow at the Center for Growth and Opportunity at Utah State University, and I'm an economist by training. But basically what that means for me now is I'm just always looking for sources of economic growth and how we can really boost economic growth. And when I saw the potential for geothermal, I started to really dive into it. I thought, well, this is it. This is such a huge important area where we need to advance in, and I'm trying to do everything I can from my current perch to unblock it and make it move faster.
All right, great. Thanks so much, everyone. So now that we're done with our round of introductions, let's dig in. There's so many puns, I'm sorry. So the first thing we want to do is kind of define the problem for the audience. Let's talk about what is geothermal energy, talk about the power generation aspect versus heat, perhaps is the first one. Folks might be aware of some of the heat pump work that's going on out there. Eli, when we met before this panel, you had some thoughts in that area. So I'll kick it over to you first.
Yeah, so thanks. Literally, like anything that involves heat from the earth is considered geothermal energy on some level, right? So there's a wide range of things that are that can be done that are sometimes called geothermal. There's ground source electric heat pumps that are sometimes called geothermal. There's low-grade heat that is sometimes piped into individual homes that if the home happens to be near a hot spring or something like that, it can be used for domestic heat. And if you go on like the geothermal subreddit, like a lot of the posts are about like those kinds of systems and stuff like that. But I think what we're all interested in here today is using heat from the earth at scale, especially to produce electricity, maybe some other process heat and stuff that can be used, again, at scale. But I think that's like the key thing that sort of unites everyone on this panel and is really being interested on that sort of scaled use of it.
Great, thank you so much. I'd like to turn over now to Carlos because we had a great discussion beforehand about why geothermal is a must. So if you could talk a little bit about that and sort of defining baseload power and the difference between geothermal and renewables that was alluded to earlier, that'd be great.
Yeah, so geothermal, let's frame the problem. I think geothermal is one of the very few things at the scale of the problem. So we need to define the problem. What is the energy transition about? Well, it's about transitioning primary energy from fossil fuels to something else. How much? Probably 30 to 40 terawatt by 2050, right? So when you look at that and you start looking for the possible sources of primary energy that can actually do it, you land with very few things. Nuclear and deep geothermal. Deep geothermal to me makes a lot of sense because it's the largest source of clean energy on Earth. It's the largest renewable energy source, right? Much more than all solar and wind combined and nuclear combined, right? It's stored energy in the planet itself. So it is to me obvious that we have to find ways to exploit this energy to be able to succeed with the energy transition. To me, we got to have high ambitions for geothermal, right? It's not just about scaling it a little bit to also be an option, to also help things a little, but we know it's very clear from all the discussions on energy transition that we're lacking the options to actually transition energy. Forget about politics, forget about economics, those things play a role too. But from a technological point of view, we actually don't have the options to successfully transition energy. But here we have a source right below us. It is hard to access, but that's what we do. We do it because it's there and because we need it. So I think geothermal makes a lot of sense for those reasons. Now we can talk about the fact that it's baseload, it's always on, it's already stored energy. You don't need storage. It has its built-in storage. You can talk about the fact that there's no fuels involved, there's no waste involved, so there's nothing like geothermal for energy security. If you build a geothermal power system, you have energy security guaranteed for decades, if not hundreds of years. And you talk about scalability. It is truly global if you can tap it at hotter temperatures and deeper depths that it's currently technologically possible.
Wonderful. Thank you so much, Carlos. And to kind of wrap up this framing the problem, I'd like to turn over a question to Tim, but I'm going to do a little screen share for this one. So I was hoping to talk a little bit about why geothermal has been geographically limited. And I'm going to pull up a very nice map that hopefully will be a nice adjunct to your answer, Tim.
Sure. Yeah, this is a funny prompt. I'll talk over the map. But yeah, I think that Eli and Carlos framed this problem well, and I'll just maybe hammer home a point here, which is that there is no shortage of geothermal energy. I mean, there's enough geothermal energy in the earth to power the world for millennia. But it all comes down to economics. And I think one question we get a lot is, well, geothermal's been around forever, why hasn't it taken off? And I think a map like this is actually quite useful in helping to explain that. Because if you think about first off, geothermal, if you've ever gone to swim in a hot spring or gone to Yellowstone or seen a geyser or something, you've seen geothermal energy. And if you think about the very first geothermal power plant that existed, it goes back over 100 years ago to 1904, when somebody in Dorado, Italy, took an area and put a steam turbine on it and actually generated electricity from geothermal 100 years ago. And so, if this is a 100-year-old technology, why hasn't it really taken off? Well, it really comes down to the economics. That site in Italy was unique because there wasn't even any drilling involved. The natural geothermal was so hot and so close to the surface that all you had to do is put a power plant on it, and there you go, and you've got power. And then as drilling technology evolved, we saw areas take off for geothermal power beyond that. So the original sort of renaissance for geothermal power happened about 60 years ago, with development really in New Zealand and Northern California and Italy. And it was because these are areas that weren't quite so good, that the steam was literally coming out of the ground on its own, but you didn't have to drill that deep to get there. Very high temperature, productive resource. And so the technology you needed to access it was not that sophisticated. And we had the right tech to do this 60 years ago. And so these resources were developed 60 years ago. And this is a good map, actually. If you look Northern California, right above the San Francisco Bay Area is where the geysers are. And you can see it's fully in a purple area where it's 350 degrees C at 10 kilometers. And in fact, it's 250 to 300 degrees C even at 8 kilometers. So it's a very high temperature resource. And so we developed all that geothermal first. But what's happened as the really good resources, whether they're in Kenya or New Zealand or Northern California, get developed, we have not been able to keep the technology curve going fast enough to go to resources that may be deeper, resources that may not flow as much, resources that may not be as hot. And that's always been the question, is how quickly can we develop geothermal technology so that, we can do it not only at the places where the steam's coming naturally out of the ground, but we can do it in places where you have to drill deeper for it and to less productive resources. And so the whole question on geothermal is, can we advance the technology fast enough to make those resources applicable? And there's really a few different ways of doing that. There's a lot of startups that I'm very excited about working on different things. One is, can we just get more effective at creating electricity from lower temperature resources so we don't have to drill as deep? And there's a company like ClimbOn that's really exciting, that's working on low temperature geothermal power conversions, so you don't have to go as deep. Another is, can we just drill a lot cheaper and a lot deeper? And I think Carlos and what they're doing at Quays is a great example of innovating in that front. If we make geothermal drilling so much cheaper, we can do this in a lot more places. And there's also different ways of getting that more flow control, making geothermal more flexible so that it responds to more grid energy. So there's all kinds of ways in which we can do this. But the whole question is, how quickly can we go from doing this where it's just in the purple places on this map to a lot more places? And I think what's exciting and why you're hearing people talk about this a lot more is the 2010s and the 2020s, because there's been so much advancement in drilling technology in the last decade, a lot of it from the oil and gas industry, and because there's all this renewed emphasis on actually achieving 100% full decarbonization, is we've got a lot of market pull and a lot of new technologies ready to deploy that are opening up the spectrum for where geothermal can be developed.
Wonderful. Thank you so much, Tim. I'm going to stop my screen share now, and I think we're on to the next segment. Carly.
Yeah, and thanks again, Tim, for that really great kind of high level view. And I think that leads very well into talking about current versus future geothermal technologies. And I'm actually curious, Carlos, when you talked about 30 to 40 terawatts of potential geothermal production, like how deep do you have to drill to get to that level of energy generation? But I think another related question that Tim touched on is how is geothermal drilling different from what's done in the oil and gas sector? So like in terms of what technologies are new or what can just be repurposed, how do you see geothermal?
Okay, so there's an important data point to realize. Whether we do anything or not, whether we are here or not, there's already 44 terawatts of geothermal energy flowing naturally to the surface. It's just been happening for 1 billion years plus. I mean, ever since the Earth was there. So when we're talking about tapping into it, we're talking about tapping of a very small fraction of the energy that's been stored there. to power civilization. And when I say 30 to 40 terawatts, I'm referring to the total primary energy that the world will probably need by the time we have to be done with the energy transition. It will come from a variety of sources, of course. It won't all come from one, but that's the scale of the problem. So to me, when you drill deeper and harder, you're doing two things. When you're drilling deeper, or let me start with harder. When you drill harder, you're doing something very interesting. You are increasing the amount of thermal energy that you can tap into. The harder the fluid, the more energy it has. And two, you are increasing the efficiency with which that fluid can actually be converted to electricity. The thermal generation or conversion efficiency actually goes up. To me, hotter geothermal is more powerful geothermal. Hotter geothermal could potentially even mean that we can repower existing power plants with geothermal. If you look at the power plant fleet in the world, the fossil fire power plant fleet in the world, which represents, I think today it's 4 terawatts, there's 10,000 power plants and they're still being built. And they are all doing the same thing. They're burning a fossil fuel to heat water. That water becomes vapor. That vapor runs a turbine. That turbine generates electricity. So what if we put aside the boilers that are fueled by carbon, by a fossil fuel, and instead get the steam from the ground, from a geothermal source? You feed that to the turbines, and you're good to go. You can do that in months per power plant. And if you employ the oil industry as the supply base, as the workforce base, as the regulatory base, you can actually move at gigawatts, if not hundreds of gigawatts per year, which is what it needs to be done. So that's what the hotter geothermal means to me, is the ability to repower power plants to really move very, very fast with energy transition. The second part is going deeper. Deeper simply means that you're able to do it in more places, right? The target is for us 300 to 500 degrees centigrade so that we can repower power plants. And if you want to do that, no matter where you are in the world, it basically means you have to drill as little as 3 miles. That's already doable in many, many places, or as much as 12 miles. That's actually not doable. Nobody can do that today. So deeper geothermal is more universal geothermal. I think those two things come together to really put forward a terawatt source. And as Tim very rightly said, it has to be done economically. So it's not just about being able to do it. You are competing with other sources, and you have to be in the money to be able to scale these. For us, it means you have to be in the 1 to 5 cents per kilowatt hour every single time. That's the only way you can actually truly scale there.
Thanks, Carlos. Thanks for highlighting that. I think really interesting opportunity to potentially convert over other power plants if you can hit hot enough temperatures to get really good conversion efficiencies and power generation efficiencies at those plants. And I guess, so we're talking, that was a good comment on reusing existing technologies, even outside the oil and gas sector. Within the oil and gas sector, I'm curious for the other piece of it, for the downhole piece of it, what exists, the technology today, good enough to enable the energy transition? Like, clearly, like Carlos said, we can't go down 12 miles, but maybe Tim or Eli, if you want to comment on how deep do you think we need to go, and do we need new drilling technologies, or how close is what you're using to conventional?
Well, there's actually a whole range of different proposed ways of doing geothermal. So there's the supercritical EGS that Carlos is talking about. There's regular, I might call it regular EGS or standard EGS. I don't know if that's fair to Tim, but that, what Furvo is doing to exploit temperatures that are not quite as hot as what Carlos is talking about. And then there's a bunch of closed loop solutions and some hybrid solutions that are using closed loop and not closed loop. And so, how hot and how deep you need to go depends on which method, which of those different proposed ways of doing things you're going for. So if you're going for if you're doing a closed loop system with a different working fluid other than water, you might hit a supercritical temperature. If you're using, say, isobutane as a working fluid, it's like 135 degrees C, and that can be very efficient for that use case. If you maybe get to 200 or something like that. So it really very much depends on the concepts, and we're gonna see which one or ones, hopefully probably multiple concepts are going to win out here, and we're going to have different solutions for all those different methods.
Yeah, I can share a couple facts that I think are interesting. I think I framed this up in the beginning. It's all about the economics, right? And there's the amount of power you get out of a geothermal well really comes down to how much flow you get, what temperature that flow is, and how efficient you are at converting it to electricity. And I think there's a lot of different things that are interested in pursuing. The reason I talked a little bit about the value of low temperature up front is the emergence of what we call binary cycle power plants, and the fact that they've come down the cost learning curve and are very proven technology that this point opens up a lot more resource. And just to give you a couple hard numbers to hold on to, NREL has done the estimates of how much this resource is at different depths. And the analysis for the resource between 150 to 200 C, which is right in the prime window for these binary cycle power plants that are now already commercially available, we have around 100 gigawatts of potential just in the United States between 3,000 meters and 4,000 meters depth. And that's something that we can drill viably today with existing technology. And you go down one layer deeper and you have between 4,000 to 5,000 meters, and that potential goes up to 1,000 gigawatts. And that 1,000 gigawatts is roughly the size of the US electric grid today. And so if we can figure out how to drill in a cost-effective way, get very high flow rates out of these wells at those depths, there's no real shortage of potential there. And that's something I think is a really big prize and opportunity worth pursuing. Now, that is all technical potential, and it's not always going to be developed because everybody knows that there's all kinds of reasons for a project not being developed, not being in the right infrastructure, not being in the right access to the marketplace. So I think it's still very important that we're continuing to develop solutions for drilling even deeper, but I don't think everybody's always aware of how close and accessible the size of the resource base is that is already within the depths of viable technology. And one of the things I say here is I tell these facts to people and they're like, well, that was true 10 years ago too, what's different? And I think the difference is that if you've been involved in the drilling sector, particularly in the technology advancements that have been pushed forward by the oil and gas industry, it is kind of wild how quickly drilling technology has evolved over the last 10 years. And you couldn't make that statement about drilling to 3,000 to 4,000 meters and doing so in an economic fashion 10 years ago. The tech just didn't exist to do it. But there's been such a tremendous learning curve in terms of drilling advancements that this is an opportunity that's just become accessible to us economically in the last couple of years. And I think that's why you're seeing so much enthusiasm about this. And I think that there are a lot of parallels to how the shale boom took off in the oil and gas industry, where you don't have to go back that far ago to 2007 and look at all of the plans in the United States to export natural gas, all of the plans to import oil. The oil industry in that time was basically written off in the United States. And now the US is the largest oil producer in the world and exporting natural gas all over the world. And that's because the drilling technology story advanced so rapidly that it was able to make that happen. And we're just in the early innings now of applying some of those same drilling techniques to the geothermal industry. And I'm expecting very similar results in terms of catching people by surprise about how quickly and transformative the industry can grow.
Nice. Oh, Liz, you sound like you have a question you want to add.
No, I was just watching the chat and the Q&A, and there were a couple of follow-up questions that I think would dovetail really well to some of what Tim and Carlos have brought up, in particular on drilling, but also on just the fact of where the state of the technology was 10 years ago, right? So we have in the Q&A a question about the redevelopment history of bottle rock power. Is anyone familiar with this? Would like to field this, maybe clarify and elaborate on it a little bit on the economics of the drilling and what's different now compared to the 2007, 2008 timeframe when that project came online. Yeah, we'll go to this one first, and then we'll go to the questions in the chat.
I can make a couple comments on drilling technology. I think the time frame of that project is interesting as well, because it is something that it's funny that the kind of emergence of better drilling technology and the U.S. being a producer of oil and gas is pretty much accepted wisdom, and people do forget that that's only really been true for the last decade, and in fact technology's continued to advance quite rapidly. I mean, I could tell different anecdotes about this, but just to make it personal, I started my career in the oil and gas industry a little over a decade ago, right when the shale boom was taking off. And I remember when I first started drilling in South Texas, our average days to finish drilling a well was 45 days. And after around 1 year of working in that field with better technology, our company was able to reduce it to 17. And that's actually gotten a lot better since then. And wells that are drilled today in the oil and gas industry, their horizontal sections are often 2 to 3 to 4 times longer than what we were drilling 10 years ago. And they're doing it in a fraction of the time that it took to drill. And so I think that there were a lot of really good technology breakthroughs and things that happened in sort of the last big wave of geothermal development in the US that happened in the late 2000s. But a lot of that interest in geothermal development was not necessarily driven by a new technology story. It was driven by the fact that people thought natural gas prices were going to be very high for a long time. States in the Western United States were implementing low-level renewable portfolio standards, and solar was still expensive. So people were willing to invest just at a higher price, but with the same sort of technology that had always existed. And in fact, it's interesting, you go back and look at that time period, because the oil and gas industry competes with geothermal for drilling services and other things, a lot of times the geothermal development wasn't really even being done with modern equipment. And it was kind of like the oil industry at the time was booming. And so there were a lot of cost issues at that time. And when the market story fell apart in terms of solar getting very cheap, natural gas getting very cheap, and at the time, no one was thinking about doing anything more than 10 or 20% of their grid from renewables, there wasn't an impetus to invest in a solution like geothermal. So I think we're talking about a very different time period now, where on the one hand, tech is quite a bit different than it was before, and we can't underestimate what a difference that makes. And two, the markets are in a different place, because you're now seeing people talk about 24/7 carbon-free energy for the first time, and that's where geothermal really shines, and that was not part of the conversation before. So when solar got cheap, that was kind of the end of geothermal, and now everyone knows solar's cheap. It's going to make up a big part of the grid, but we're trying to figure out how do we decarbonize the other hours. And I think geothermal is going to be very competitive in that environment.
Yeah, I might add that Bottle Rock is one data point as well in the Geysers, which actually has been viable and continues to be viable.
And just quickly, Carlos, could you maybe explain, so Tim mentioned Geysers is just north of San Francisco area. What is Geysers? Is this just a hot spring, or can you give a little background on that facility?
It's a geothermal field. I think it's the largest geothermal field in the world today. It's about 3 gigawatts, or it was 3 gigawatts. It's been declining, but it has a world record for one site geothermal capacity. And it just, the geological setting coincides to have a very rich and prolific hydrothermal resource. Hydrothermal is one of many flavors of geothermal, right? The more conventional one. So the Geysers have been operating for a long time, and they continue to be viable, and Bottle Rock in particular. I don't know the specifics on Bottle Rock to be able to speak on what specifically happened there, but if I look at the geological setting, the location, actually it is viable. It is very viable, and it is the largest in the world today. But I cannot emphasize enough what Tim said. Technology changes, and when it does, everything changes. What was not viable becomes viable. What was uneconomic becomes economic. What was something not to be looked at out there in the corner becomes the main actor. And that's the best we're doing in Kuwait. We think technology will play a huge role, and it's not binary. There is a very natural staircase to scale geothermal with all of these flavors. But I like to bet to the holy grail of geothermal, the terawatt geothermal, because I think that's the true potential of geothermal. And we're going to try to make it possible.
Maybe I know you've got another question queued up, Carly, but just real quick off of what Carlos said. Sorry to interrupt. So Tim mentioned getting the drilling times down from 45 days to 17. Can you talk about with quays and going deeper, like what you estimate the drilling efficiencies would be?
For quays in particular, okay, so I need to say that quays drills to basement rock conventionally. So we have to get from the surface to the basement, which the basement is a geological layer below the sedimentary basins where we live. We have to get there conventionally for many, many reasons. And then we do millimeter wave drilling from then on. And it's really not about drilling very fast. It's about drilling very consistently. You know, when you look at why does it cost so much to drill deeper and deeper and deeper, it has to do with how much non-productive time you incur. Picture this. You're going to spend 5 days running pipe. You drill for a few hours. The drill bit wears. You pull days. You change the drill bit, go in for days. You drill for a few hours, and you repeat that. It becomes impossible, exponentially impossible. And the drill rig is commanding rates of $100,000 per day in some cases. So it just grows astronomically in cost, not because you're not drilling fast enough, but because you're not drilling most of the time. So the quays approach is to fundamentally change the physics. There's nothing to wear, nothing to change over, and we just burn consistently into the ground, not too fast, not too slow. We're going at 5 meters per hour, 10 meters per hour, which is not earth shattering, but we just do it consistently, day in and day out until we get depth. And that drastically changes the economics. We're talking about $1,000 per meter to drill, which is what oil and gas does today in some formations. In some, they do cheaper than that. In some, they do more expensive than that. But if you didn't do what Quays is doing, by the time you're trying to drill a 10-kilometer hole, you're getting into $100,000 per meter, you know, by the time you're really, really deep. So it really makes a huge difference.
Awesome. And that was one of the places I was going next, which is what are some of the challenges around each step of geothermal? You know, they're in drilling, clearly as you get deeper, things get harder. Carlos talked a little bit about that in terms of sending fluid down there to get the heat out. And maybe that's something that we could move on to next is what are the different ways to send heat down or fluid down so it heats up and you can take that out and generate power. Tim, you look like you've got something burning, and then maybe we can jump over to Eli to comment on some of the different paradigms out there.
Sure. Well, I was just going to comment on what Carlos said, and it's something I feel like a lot of folks that Carlos knows well, I know well. One of the reasons I'm excited about what Quays is working on is that focus on consistency, and because it is something that is interesting that folks outside the industry, and I spent years working as a drilling engineer, don't always appreciate, is that most of that improvement comes from just being able to deliver day in, day out without having to come out of the hole because something broke or without having to address other issues. And it is something that's interesting that I think when people first look at geothermal, they're like, oh, you got to drill 100 times faster than we drill today. And there's actually diminishing returns to how quickly you can drill. But if you can figure out how to do so consistently without having to the way Carlos described, that's where the big prize is. And actually the vast majority of the enormous improvements that have happened in the oil and gas industry come from delivering on that consistency, which is something that is difficult in geothermal because we're dealing with different rock and higher temperatures. But it's an engineering problem that can be solved in a very straightforward manner, which is exciting. But just wanted to drive forward that point on what drives the economics there.
That's great. How do you get things to stop breaking down downhole as frequently? Any quick comments?
Yeah, I think there's a lot. I think it's understanding what rock you're drilling into and what methods are most effective for that. I think it's coming up with ever more robust materials and electronics that go down that hole. So you look at why you have to stop drilling. It's because there's been issues with wellbore stability that you have to address. So your flow circulation that you have to address. And we need to develop tools for that. It's because the motors that you're using or the downhole equipment you're using wear out and break down, especially under high pressure and high temperature. It's because the electronics that you're using downhole can't hold up to those temperatures and go out. So you can't actually measure what you're doing anymore. And you think about solving those things systematically, or as Carlos and his company are doing, design an entirely new system that doesn't have those same drawbacks, and you can get very meaningful results. And it's actually something that I don't think people always understand. If you drill slowly but consistently, you can actually have very cheap wells. And that's a bit what the oil and gas industry has done very well over the last decade.
Yeah, you can make things stronger or you can make things simpler. Both will work to get the result. You know, a lot of people are ruggedizing things, making better drill bits, better electronics, and that will work. That will pay off over time. We are taking a blank slate and saying, let's make it simpler. Let's make it so simple that the probability of things breaking is very low, actually, and we recognize those very few things.
Awesome. So Eli, do you want, okay. I feel better about drilling, and if you have more comments or questions on drilling, put them in the Q&A and chat. But maybe Eli, that second piece of it. So harvesting the heat, bringing it back to the surface. What are some of the different approaches there? And I'd love to hear your commentary on that as well. Oh, you're on mute. Yeah.
Of course, somebody had to do it, and it was me. Okay. So drilling is only half the problem, right? You have to get to heat, and then you have to transfer that heat somehow to your working fluid. And in conventional geothermal, this sort of like the heat reservoir or the transfer reservoir is already made for you. There's porous rock, there's a layer of porous rock where the heat is, and then there's capstone rock above it. And so it sort of traps the heat in, you inject fluid in, it gets hot, and then it comes out another well. And that's already made for you. With EGS, with essentially both what Tim and Carlos are doing is they're creating that underground, that porous section through techniques that we've learned in the shale fields of fracking. So being able to create that fracture network underground, deep underground, and using that to transfer the fluid is one way to do it. Yes, the other way to do it is to use a closed loop. So you still have an injection well and a production well, but instead of having a fracture network in between them, you have a set of pipes that transfers the working fluid between the two wells. Now, the downside of this approach is that you don't have as much surface area to transfer heat, and it's very surface area is very helpful. If you're trying to harvest that heat energy. The upside arguably is that you get to use a different working fluid, potentially supercritical CO2 or something else like isobutane. And if you can do that, then maybe there are some advantages in terms of you can reach a critical temperature without having to go as deep. And then there's another hybrid approach that it relies on a closed loop with some exotic working fluid, but also does some additional subsurface engineering to create additional heat accumulation and use a heat exchanger to impart it to the fluid. So there's a bunch of different approaches, and I'm excited about essentially all of them. I want to see let's try all the things and see which ones stick. I think success in one of them will probably help all the other approaches as well, because it'll sort of be a proof of concept and prove that you can extract energy at scale this way.
Great. Go ahead, Carly. I just saw a couple of questions in the chat that kind of go to a little bit of what you were saying earlier, Eli, and I'll throw them out to the whole panel on kind of the regulatory and the politics around geothermal, right? One of them was more of the market liking growth, and that solar and wind are not like looking to completely replace fossil fuels, so maybe that's part of why the market is enjoying them so much. And there was another question related to kind of the local politics, and in particular, Tim, we talked a little bit previously about sort of the concerns with induced seismicity. So I was wondering if you could speak a little bit on that one, and how your approach for what you're doing at Furvo, the regulations that make sure that induced seismicity is not a problem.
Yeah, I mean, a couple of things there. I actually want to start maybe by building on one point that Eli talked about the importance of flow and different ways to access the reservoir. The other thing that I find very exciting and that we're employing at Furvo is developing new techniques for horizontal drilling. And so you think about this, it's all about your energy output you can get per well. And if you're going to drill wells, it's expensive, you got to get more bang for your buck. One of the big downfalls of geothermal historically has been, by and large, you're drilling simple vertical injection and production wells. And these wells may be only 8 inches across, so you're not really talking about giving yourself that much opportunity for flow to go between the wells. What our company is working on, and what others like the Forge project being led in Utah by the Department of Energy, Deep Geothermal in Canada, which we're big fans of, is focused on that horizontal drilling aspect. So actually getting that flow from your injector wells to your producer wells, not just from a simple 8-inch pole that might be very far apart from each other, but actually doing it and we now have the technology to drill tens of thousands of feet in a horizontal direction. So you're going to get commensurately a lot more flow from those systems than you would otherwise. And so that is a big thing. You know, a stat that's kind of mind blowing in the United States, we drilled about 200,000 horizontal wells for oil and gas over the last 2 decades. And we are soon to be at 2 or 3 horizontal geothermal wells. I mean, this is something that's very new. And I think it's fascinating that we've gotten this far without adapting this technology over, but it's not easy to do for a whole host of engineering reasons. But we're right at that cusp now where it's going to make a big transformation. Just wanted to talk about that from a technical standpoint. In terms of acceptance of geothermal, it is interesting. And what you find is, you know, I've been all over the world to different projects from development in national park in Kenya of geothermal, where they've worked on actually adding a spa and resort area that's right inside of a big wildlife center, right adjacent to the geothermal plant, to places like the Blue Lagoon in Iceland, which is very similar, where it's a spa is co-located with the geothermal plant. You know, I've also visited a geothermal plant in downtown Munich, which is quite fascinating, an area that obviously cares about their environmental footprint and aesthetics and other things. And generally what you find is if the geothermal industry does a good job of explaining what we're trying to do, there's a lot of local acceptance there. Geothermal plants from a land use footprint are a tiny fraction of land use of other renewable energy resources. And in certain areas, that's very important to people. And once the construction phase is over, a lot of times you're left with kind of a nondescript looking almost warehouse that can generate enough power for entire cities. And so there's a lot of things from a land use footprint that we're finding environmental communities are very excited about. From other things that we have to be aware of, where geothermal, the industry has not always done such a great job in the past, there are other local environmental impacts. You still have to do your full construction phase correctly. You have to make sure you're monitoring the local air quality, the local water quality, and the geothermal industry has a good track record, but clearly incidents where those have caused issues. And then one of the big ones that is top of mind for a lot of people is the issue of induced seismicity. And I think this is something that happens a lot, in particular because of fears from the oil and gas industry, where, you know, whether you're in Oklahoma or West Texas or elsewhere, there's been a large increase in Cuban-induced earthquakes. And people worry that if we're going to apply similar techniques in geothermal, you know, what is that going to do? Is that going to cause major issues? And I think one of the things that I like to point out in terms of the geothermal operation here that's quite a bit different, a lot of the seismic activity associated with oil and gas comes from the fact that they bring up a huge amount of wastewater and they have to re-inject that into the subsurface in large quantities. That ends up shifting sort of the stress state and adjusting how the stress state is, and that can cause earthquakes like some of the ones we've seen in Oklahoma. Geothermal is quite a bit different in the fact that what we're doing is flowing water from an injector well to a producer well and then recirculating it. So you're not actually extracting any fluid or putting any fluid net into the ground. It's really just recirculating the same fluid. And so it doesn't have a lot of those same stress issues that have caused some of the earthquakes associated with oil and gas activity. So I think there's certain structural things about geothermal that make it a lot safer for a lot of environmental reasons, including when it comes to induced seismicity. But even beyond that, one thing that you'll find pretty consistently in the US and around the world is regulatory regimes and support structure where the geothermal industry gets way more scrutiny than equivalent oil and gas operations. I know this is something Eli's written a lot about, so he's probably the right person to talk to. But if you want to drill a geothermal well in the United States, you have to go through a huge amount of redundant NEPA reviews and environmental processes that are essentially all excluded if you want to drill an oil and gas well. So even in 2021, in the midst of a climate crisis, it's way faster to drill an oil and gas well than it is a geothermal well, strictly because of the permit regime. And this also applies from an induced seismicity standpoint. There's clearly been many examples of induced earthquakes from oil and gas activity in the US. While we fortunately have not had a major issue with earthquakes from geothermal activity in the United States, and yet geothermal projects have to go through a very strict and rigorous induced seismicity protocol in order to greenlight project development, and the oil and gas industry does not. So that's one of the big barriers from a policy standpoint. that we're dealing with that I think Eli testified to Congress about how important this discrepancy is.
And if I could, I'll just address the question or the point from the commenter about, isn't oil and gas, aren't they going to hate this? Aren't they going to shut it down? And I think it's quite the opposite, right? I think this is a huge opportunity for the oil and gas industry to basically, find their next, multi-trillion-dollar business, take their existing skills that they have and apply them to geothermal. And they're off to the races, and they're no longer they no longer face a threat from climate change. And so it's a tremendous opportunity, and both Tim and Carlos come from the oil and gas industry, and they have made that switch. And I think it's just once as it starts to sink in the industry, and it's already starting, I think that people from oil and gas are going to really embrace geothermal. And I don't think it's gonna face headwinds on that front at all.
Thank you, guys. We got one real quick follow-up question in the Q&A, and I'm going to direct this one to Carlos because it was about the difference between the more shallow porous rock and the deeper rock. And you had brought up previously an example for induced seismicity with South Korea when we chatted. So I was wondering if you could kind of talk about the old geological rock versus the younger, and the related issues there.
Yeah, this must be. Yeah, normally hydrothermal is in sedimentary basins, most of it, right? And oil and gas is mostly in sedimentary basins as well. The basement is a relatively new frontier for humanity. I mean, it's very hard to get into it. It's very hard to do things in there. There's exceptions. There's oil and gas in the basement, and there's geothermal in the basement, but it tends to be the minority of it. So I think when we move into that new frontier, many things change with respect to oil and gas. So oil and gas is a good analogy. It's probably the closest analogy, but it's not a perfect analogy because oil and gas is not a basement rock operation. So when you're talking about drilling in the basement, when you're talking about wellbore control, when you're talking about inflow control, when you're talking about a blowout prevention, when you're talking about all of the things that oil and gas talks about for developing oil and gas resources, those things don't translate one-to-one or actually very weakly to the basement. And that's where we find opportunity by doing things a little bit differently. So to me, we can do air drilling in the basement, for example. That opens up some avenues. And a lot of geothermal drilling is done with air anyway. We can do fracking a little bit differently because you are in different rock. The rock mechanics are different. There's actually a lot of natural fractures already there. They just have been closed by the lithostatic pressure, but you can open it up with fluid and prop them open with frac. You're not creating new fractures, you're just opening what's there. So I think we need to allow ourselves to realize that this is a new frontier and there's plenty of room for innovation there to do things differently. And the price is there, right? The energy transition requires this energy, and this is a source that can do it. So I think we got to do that. I think the other part of that is that we need to learn from other industries, not just oil and gas. I mean, we've talked about the people in oil and gas, the regulation in oil and gas, but the mining industry is actually quite interesting too. They drill a lot for a living, and they drill into the basement quite a lot. So what can we learn from those industries? Surely we're targeting our technology at them, and we're learning from them. How do they do their drilling? How do they do fracturing? How do they create space down there to mine ore in their cases, or to mine heat in our case? So let's recognize it for what it is. It's a new frontier, and there's plenty of room for innovation and solving challenges in that frontier.
Maybe to weave in one more mining thread, because I saw a question in the Q&A on controlled thermal, which my understanding is a conventional geothermal play in California in the Salton Sea that's using lithium extraction as a way to offset or just make it additionally profitable. I'm curious if anyone has comments on that project. Okay.
Yeah, I could comment. I'm a huge fan of their effort, and there's similar efforts going on in Germany and a couple other places around the world right now. It's interesting because geothermal, having mineral content in a geothermal fluid historically has been all bad. It adds to complexities in handling the fluid. It adds increased costs. And it's really been only very recently where that, you know, the energy transition is doing this in so many places. It's turning challenges into opportunities. And it turns out one of the minerals that is found in very large quantities in geothermal fluid, particularly in the Salton Sea where the Controlled Thermal Resources Project is lithium. And I think this is something that, you know, a lot of people want to know why now? Well, you know, the technology to do direct lithium extraction from geothermal brine has been around for a while. There's some questions about scaling it up, but it's mostly a proven technology. And it's only been in the last few years where we've seen this massive increase in interest from lithium, because it will be the thing that powers the electrification of our transportation sector. So you've seen this 5x run up in lithium prices. You've seen the amount, the gap in supply and demand as every company and country announces their new electrification forecast for lithium really increase. You've also seen the US government get really interested in this because they deem it a critical mineral. You know, if we're going to be basing our economy in the future off of lithium, all of a sudden it becomes interesting from a national security standpoint to make sure we have our own supply. So a lot of companies, Controlled Thermal Resources is one we're very excited about. Other ones that are more on just the technology side, like Lilac Solutions, are very exciting on coming up with better methods for this lithium extraction, are going after this opportunity for the first time. And what this is going to do for geothermal, by and large, is it's going to add, you know, yet another revenue stream and yet another value driver to what we can do, which is going to open the door for more geothermal development. And so I'd say we're watching these companies with great interest. I think it's a bit of a race right now to see who gets first to market, but the prize is just massive. And it's all about scale up of well-known technology, where we're now just seeing the market environment transpire for a strong demand of lithium. And if we can turn one of the traditional geothermal cost centers of handling these materials into a geothermal profit center, that's just going to open the door for way more development. It's something we're quite excited about.
Just to follow up on that, the Department of Energy is doing a grand challenge on geothermal and lithium right now. So hopefully we'll see even more technologies come out of that effort as well. All right, Carly, I know you have some Elko questions.
Well, so there's a lot to talk. It all comes down to cost, like you guys have said multiple times, which is fantastic. And there's two ways we could take this. Either comments on what are some of the costs beyond drilling that influence a project, you know, because a great resource does not always equal a great project. I think I've heard that a couple of times. And so when we talk about the levelized cost of electricity, LCOE, what are some of the factors, technological or otherwise, that really influence that number? Carlos already gave his estimate. I would also love to hear from Tim and Eli where you think geothermal power is going to come in at for cost of electricity. Please kick us off, Carlos.
You want me to start?
Oh, you were unmuted.
Yeah.
You can pass it. You can pass that off.
I mean, he could restate the cost prediction as well to kick it off.
So, I mean, to me, there's nothing more compelling than terawatts of clean power in the 1 to 3 cents per kilowatt hour. That's the goal, right? That's what changes the world. That's what enables everything else. It enables electrification of everything. It enables heat at point of use. It enables the energy transition, right?
And is that just drilling costs, or do you need other elements to come into?
That's LCOE, 1 to 3 cents LCOE. So that, very broadly speaking, is the subsurface development that includes drilling, completions, the surface gathering systems, and then the power plant, right? Those three components are roughly what it takes to go from heat in the rock to electron in the grid. Roughly speaking, the power plant is half of that. Power plants are expensive. Now, that's why I talk so much about repowering power plants, because they're built, they're there. There's thousands of them. Let's just use them. It's silly to throw them away. This is 100 years worth of infrastructure that we humans have built. And we're in a pickle to transition energy. We must use them. So half is the power plant, the other half is the subsurface development, including operating and capital costs. The drilling is a big portion of that, unless you're talking about shallow geothermal. You know, if you're talking about shallow, you can repurpose existing technologies, and they've gotten quite competitive. So it actually starts to make sense. But if you're trying to untap 90% of the resource worldwide, where we're talking about higher temperatures and higher depths, then drilling is going to be almost the other half of that. So if you attack that, you're going to get in the money in many, many, many places. It's not the only thing you need to do. The heat rates are important. Interestingly enough, the heat rates, the stimulation, the fracking, it's actually not an expensive operation compared to drilling and power plant build out. But you need the performance. You need the watts coming out of the ground to actually pay back your investment over 20, 30, 40 years. So that's why we talk about high enthalpy. We talk about a 50 megawatt thermal per well. We talk about repowering power plants, because all of those things systematically attack every single one of the cost levers that will really make a difference to drive the cost down to 1 to 3 cents per kilowatt hour.
Thanks, Carlos. All right. Tim, please.
Yeah, sure. I love this. Is a great question. I can tell you what we see in the market right now. There's been 15 power purchase agreements for geothermal signed in the United States that have been publicly announced since 2020. And the average price is at $68 a megawatt hour. And what we're seeing is customers, by and large, are willing to pay that because a round-the-clock 24/7 product that doesn't have any carbon emissions with it is worth a lot more than other types of energy resources. But that number is not like for every buyer. And I'll say even the buyers who are okay with that number and have these big decarbonization targets, you know, that's like, okay, we'll do 10% of our portfolio or 5% of our portfolio with that cost number. The thing that I think we want to see is if you can actually move that number down into the 50s in the interviews we have with customers, that's just an unbeatable price for around-the-clock carbon-free product.
Is that delivered or generated?
Delivered, yeah, which is pretty comparable to your delivered cost, depending on how you're doing it in most jurisdictions, which is kind of exciting because then, you know, it's not that our industry needs to have this like 10x cost reduction. It's like, you know, if we figure out how to cut 20 or 30% out of the cost over the next couple of years, we're going to go from being that 5 to 10% of a customer's portfolio to a huge mix of it. And that presents a good opportunity. And one thing I want to drive home too, again, it's about the importance of policy and finance in this world. If you look at like the NREL cost structure on geothermal and other technologies, one of the largest cost items for geothermal is what they consider to be the cost of financing. Because they, unlike other renewables, they look at the track record of geothermal and put 8 to 10 year construction timelines in there with a high cost of capital throughout that entire time. So you end up with a situation where 30 to 40% of the cost of a geothermal power plant is just maintaining the financing over that long time period. And there's no real reason why it has to take that long. If you look at a time analysis of what goes into most of that 8 to 10 years, the majority of it is actually waiting on redundant permits. And so, you know, we can get a lot of the way there with better technology. We can get a lot of the way there with better policy, but we don't really have that far to go in terms of, you know, I think if we hit the targets Carlos was talking about, 1 to 3 cents a kilowatt hour, which I think is reasonable in the long term, it's going to be unbeatable, but we're going to be every customer's favorite energy resource if we can even get down into the low 50s, which I think we can do very easily with the right technology, innovation, and policy support in the next couple of years.
Wonderful, thank you. And then to wrap our webinar with T-minus 1 minute, Eli.
Yeah, I think we're going to see a gradual snowballing throughout this whole decade. You know, every improvement in geothermal technology will make all the other improvements that we need in geothermal technology that much better of an investment. So if you improve mechanical drilling, it's like, okay, then that the incentive to do something about turbines and make them better for geothermal, like that improves as well. So I think there's going to be a snowballing, and it's going to just, by the end of the decade, I think it's going to drive costs down significantly. And I agree with Tim. This is going to be like another fracking boom. It's going to catch a lot of people by surprise.
Wonderful. Thank you guys so much for all of your time and for being part of this webinar today and educating our audience. Carlos, Tim, Eli, much love. And to everyone else, if there's any follow-up questions, you can reach us, liz@primemoverslab.com. Right, thanks so much, guys.
Thanks, everyone.
Thank you.
Thank you.